All right, and we are recording. All right, so what we're doing today, I do have, I have a few starter questions for you guys. Right, so 3 starter questions. We'll go into those in a moment right before I get to attendance. Let's go over top scientists. So something I traditionally do for quizzes. So we'll start with that. Is if you see your name on this list, then you did really awesome on the forces quiz. Yeah, so really good job. All my top scorers. Okay. Our main thing we're going to do today is the Mechanical Advantage Lab. Okay. Now, if you're in class, and a few days ago I gave you guys, well, 2 pages. One of them looks like this. You guys got this page? Okay. Does anybody need this page? Anybody need this page? Okay. I have a few extra, so if you do, just let me know. Oh, you? All right, then, okay, well, I wanted to lead into that lab with an animation, but having some technical problems today, so sort of skip that. Okay. I'll give you guys some time in class to do a lab write-up, and I'll remind you guys what AP's looking for that. I got this nice checklist of what AP's looking for in a write-up, so we'll come back to that. And then we'll have some time at the end of class to, well, probably do some more college physics questions, but we'll see when we get there. Quick reminders, tomorrow we're going to go over AP Classroom multiple choice, so make sure you guys have turned those in tonight, or at least before you get here tomorrow. And then you guys remember also I assigned you guys a few college physics problems, so turn those in Friday. Now, remember, and I know I've made this point a few times, but I'm only assigning you 5 problems for a few reasons. One is that this is in addition to AP Classroom, and I'm also having you guys do take-home open notes quizzes. So that's like a lot of stuff at home. And also, I know you guys have other things to manage, like other AP classes and like part-time jobs and a bunch of other stuff going on. So the stuff that I'm assigning to you guys is really like a minimum you'd want to do. Now, if you feel super comfortable with stuff, like, oh yeah, I totally get this, and set this up, easy, check the solution, yep, everything's working out, then you're good. Right? On the other hand, if you're like really struggling with this stuff, then there are plenty of other practice problems, and these are all resources that are on Google Classroom. Just remind you guys that all the stuff is here, all the solutions are up there. So I will let you guys, of course, manage your own time and how you study for this class, and how you manage that with all the other stuff you're doing. Let's take a look at these 3 questions. So first question, a kid starts from rest and slides down the frictionless slide. Ooh, frictionless, that's a nice simplification. What basic conservation of energy setup would let you solve for the speed at the bottom of the slide? You guys remember like this table that we did? You guys remember how over and over this class, last few days, of course we're doing conservation of energy this week. The thought process this week is that, okay, well, if energy is conserved within the system, then you can rope off all the objects in the system that, so there's no work done on or by the system. Then you can set up an equation like this and say the energy at one point is equal to energy at another point. And then over and over and over, we've just been using these same 4 building blocks, right? There's, these 4 right here. Work, like a transfer of energy. There's potential energy, like gravitational. There's kinetic energy, energy of motion. And there could be energy stored in the spring, right? Just use these same 4 building blocks over and over and over, whatever is applicable to a particular problem, okay? Next question is, let's say an elevator is moving up at some constant velocity, like 2.5 meters per second. Let's say the elevator weighs 900 newtons. What is the power output of that motor pulling up this elevator? And then the 3rd question, which is going to lead into the lab today, is, you guys see this fancy looking rig right here? Right, got a guy with trying to lift this block, right? Maybe it's like 50 newtons. So this block here weighs 50 newtons. He's pulling it up. What is the tension in that rope? Right, so while you guys are thinking about those questions, I will be grabbing attendance. Ooh, I think everybody's here. Yeah, all right. Yeah, flip out of here. Checking with you guys. Does anybody think they feel pretty good about all three of those? All three? Okay, let's start with these one by one then. Okay. So first question, the kid in the slide. Okay, so he's sliding down a frictionless slide, so no friction losses. That's nice, right? What's the conservation of energy setup? Now we've done a ton of energy conservation setup. We did most of these on Monday, did a few of these on Tuesday. Also, a bunch of these college physics problems, we had to start off with something that looks like this. The sum of energy at some point in the system equals the sum of energy at a different point in the system, right? And then these energy bits, all we're doing is, again, just choosing from this checklist of 4 possible building blocks. Now, there are some other building blocks we might add as the class goes on, but this week we just care about these 4. Okay? So, because what kind of energy does the kid have at the top of the slide? Potential energy, MGH. Right? So that's how you can quantify the number of joules due to height, right? MGH. What kind of energy at the bottom of the slide? Kinetic. And doesn't the formula for that go like that? That's it. That's the whole setup. Oh, yeah, Trey?
If you're solving for speed at the bottom of the slide, you also solve for V.
Oh, right. Yeah. So this would be the setup. You would solve for V.
Oh.
Yeah. And then it does always end up being the same answer. Is that, well, or I should have asked you guys, but you would have said this anyway, right? That goes away. Okay. You always get this just for a basic no frictional losses and also start from rest. It always comes down. This is a good thing to hold on to, right? Okay. Now, something I want to mention about this though is that, you know what else this setup exactly applies to is Galileo dropping stuff off the Leaning Tower, right? If Galileo drops stuff off the tower, how fast is it about to hit the ground? That's exactly the setup too. This setup could explain how fast this ball is going to crash into the ground, right? Okay. And think about that. It's like, come to think about the slide. I didn't actually tell you the geometry of the slide. I didn't tell you whether it was a really steep slide or whether it was a long and shallow slide. Right? All I did was mention something about the height of this thing. So what if I had a height of this leaning tower versus a height of a steep slide versus the height of a kind of a shallow slide? Okay. Now again, assuming no frictional losses on any of these 3 different scenarios, okay, let's say these all have the same height. Okay. And let me just make up an answer here. Let's say that the final velocity for Galileo's, whatever dropped here, it's called 25 meters per second. I don't know, just make up a number. Okay. Now, if the steep slide has the same vertical height change as the leaning tower, what is the speed of the kid at the bottom of this slide? Yeah, 25. Did I say meters per second? I meant to say meters per second. Okay. And what about the long shallow slide? What's the speed of the kid at this slide? Yep, 25 meters per second. Okay. So notice that what's really important is the height change, not necessarily other aspects. Okay. Now, if there was friction, then friction would act along the entire length of this thing, right? So where do you think the kid would be moving faster if there was friction? Right? And let's say like the same materials to build the slides. Right? Would he be moving faster at the bottom of the middle one or the bottom of the steep one or the shallow one? You're right, it would be the steep one. And from an energy conservation point of view, why would that be?
Shorter, less friction loss.
Yeah, less friction loss because this length here would be shorter, so that friction force would act over a smaller distance. In fact, we did this exact setup back on Monday. So we were including friction. So so it starts with potential energy, right? Ends up with kinetic energy, obviously, but also plus force times distance of for the energy loss, right? So here's the energy you start with. Let's call it maybe 100 joules, and here's what we'll take. Maybe it's like 80 joules and 20 joules, something like that. Okay? But this length L, right? That's the distance that the friction acts on, which is a lot longer for the long slide, isn't it? So you're right. If there was friction, the kid would be moving faster at the end of the steep slide than the long slide. But if there's no friction, it's the same. Right? You guys see that? Okay. Something else I want to mention about the slide is that you're usually not given the height change. I mean, you could be, right? You're usually given you're usually given the length of the slide and the angle it's pitched at. Could you guys solve for h if you knew these two things? Yeah, what it would be? H is equal to
Sine theta.
L sine theta. Oh yeah. Isn't that be true? Trigonometry, right? Right? You guys ready for next one? Elevator moves up at constant velocity, 2.5 meters per second. Say it weighs 900 newtons. What's the power output of the motor? What do you think?
I got 2,250 watts.
2,250 watts. That sounds about right. Anybody else get about 2,200 watts somewhere in there? Okay. Okay. So let's go through. So it says power output. Okay. What's one of your guys' definitions for power? Okay. Yeah. You remember the tricky one? Yeah. Let me lead into that. What is sort of the definition of power? Isn't it like a rate of work or rate of energy?
Work over time.
Yeah, something to do with like work over time, right? Something like that. Okay. So that's kind of definitionally how to think about power, like the rate of work, rate of energy. Okay. Now you could say, oh, well, I know what work is. Work is just force times distance, right? Okay. And maybe if I did a free body diagram for this elevator, if it's going constant speed, that would be equilibrium. So the force up, like this tension pull up, would exactly balance its weight down, wouldn't it? Okay. So anyway, something to do with like a force, maybe a tension force, right? Times however far you're pulling it up. And then there's like some time interval to do that. Guess how this is equal to this? Right? And then now, Bella, you were just saying this next step, where is this leading to? What I'm about to write here? Force times velocity, right? Because doesn't this right here? Distance over time? Aha, that is velocity, isn't it? Okay. So if you ever have a situation where an elevator is going up at constant speed, this is a prime question: is what is the power output to lift it at constant speed? Right? Now the trick is this would be really good for constant speed, wouldn't it? But what if the elevator was actually accelerating upwards? Well, you'd have to do, if you wanted to apply this, you'd have to do average speed. So you could apply this, it'd just be a little bit trickier. Maybe a couple extra steps. You guys see that? Yeah. Okay. So AP does not give you this formula, so it's good to have this in your back pocket if you need to pull that out. Right? Any questions about the elevator or the slide? Right. Right. Now this guy, he's got some fancy pulley system going on here. Right. This weight is, well, it weighs 50 newtons. Right. Let me ask you guys a side question. What is the mass of this thing? Pretty close to. What do you think, Kevin?
5.
5 kilograms? You guys like 5 kilograms? Yeah, because 5 kilograms times Earth gravity would give you about 50 newtons, wouldn't it? Ooh. Okay, so mass 5 kilograms, weight 50 newtons. Okay. And the actual question is, what is the tension in the string, right? Okay, simplifying assumptions, massless, frictionless pulleys, string, all that. Here. I guess rope, I call it rope. Okay. What is the tension in the rope? Who thinks they have a pretty good guess what the tension in that rope is? What do you think?
50 newtons.
Okay, so it is true that there has to be a 50 Newton upward force, right? 50 Newton upward force. You guys remember back when we did the spring scales lab? It was like it was really like 10 mini labs. We're looking at what happens to a force? This, that. Okay. What if I had a couple of spring scales and this has a hook on it, right? Okay. And then let's say this is vertical, so gravity's pulling down this way, right? Okay. So I've got this thing under the influence of its own weight, right? And let's say it weighs like some amount. Okay. Then I hook another spring scale onto it. Now we did this. I'm just reminding you guys what you guys already did a couple weeks back. Right? Right. Remember how the force divvies? Right? Like, so for example, if this thing weighs like 10 newtons, wouldn't it split like 5 and 5? Or maybe it's like 6 and 4, 7 and 3. But the two upward forces add up to the weight pulling down for equilibrium. Okay. So if you look back here, let's say we focus on maybe this is going to be called a movable pulley. I'll show you why. I've got this actually rigged up next to me too. Being a lab today. This can move up and down. If I do sort of a free body diagram on this, it's got 50 newtons pulling straight down. Right? But aren't there sort of like 2 strands of rope pulling up? Ooh, so what would be the tension in each strand to balance out the 50 newtons? It would be 25, wouldn't it? Huh. And if there's one tension in this rope, again, assuming no frictional losses, all that stuff, okay, how much force does this guy have to pull with? 25 newtons, right? To either just keep it in place or to move it up at constant velocity, right? And either of those cases would be equilibrium, right? Yeah, he only has to pull with like 25 newtons. Okay. What if his maximum pulling force is like 30 newtons? At 30 newtons, he kind of peters out, like, oh, I'm too weak for 31 newtons, or yeah, too weak for 31 newtons. Or I can't even lift this weight. 50, that's way too heavy. Can you lift it with this rig? Yeah, because that would be with his capacity, wouldn't it? Like 25 newtons? Oh, I can do 25, right? Right? Yeah, so you can actually lift something that'd be heavier than normally would be able to. That's called a mechanical advantage, and that's what we are going to switch over to right now, mechanical advantage. Right? So now you guys have, of course, this lab page. How we're going to be doing this is we're going to break up different mechanical advantage systems. We'll do some calculations. If I wanted to, I really could have expanded this and given you guys more tables to write more data. So as we go through this, I might jot some extra notes on the side. Right? But the back of this, I specifically left blank so that you could make the lab write up. And here, just do a little flashboard here just to get you guys thinking about this ahead of time. You guys remember what AP is looking for in terms of the labs. There's some questions you want to tackle. I'll throw you guys a couple of recommended questions. So help you guys figure one out. AP is very interested in what measuring equipment do you need to make the measurements that you're interested in gathering, right? Maybe spring scales, possibly. Do you need a protractor? Do you need a meter stick or a ruler? Do you need a balance? Do you need a stopwatch? Right. Now we're not going to need all those things today, but maybe something in that list. You're looking for a procedure to gather the data. They're just looking for a handful of steps, maybe like 3 to 6 steps, somewhere in there. Like, how am I going to go about gathering the data? Okay. Then once you have that raw data, how are you going to analyze it? This might be an equation, this might be a graph, right? Something like that. Right? And then what conclusion can you draw from that? Okay. Okay, so that's just a reminder there. I'll put that up later too. Right? So let's talk about my original intention was to show you guys an animation of some pulley systems where they talk about the physics behind us. Since my computer's not really working for that today, then we're going to do this a different way. Okay. So let's talk about these pulley systems from a conservation of energy point of view. Because already you guys see that this guy's getting what's called a mechanical advantage. He only has to input half the force that he needs to lift something very heavy. Right? 25 newtons pulling to lift something that's 50 newtons. Ooh. How does that gel with this conservation of energy, right? Where the energy should be conserved within the system. So the sum of energy initial equals the sum of energy final. Right? I mean, this setup has been, you guys have seen this way at least 20 or 30 times the last couple of days, right? So if I go to my building block checklist, right, I've got these to choose from. Right? Well, let's see. I don't see any springs involved, at least not in the picture, so I'm not really worried about that one. I'm not really interested in motion. I could see I'm not interested in changing the speed, right? It can either be just held in place, or if it's going up at constant speed. Guys, if it's going up at constant speed, is its kinetic energy changing? No. So if I were to include something like this in the system, it would just cancel out on both sides because the V is the same on both sides. Okay, just gonna cancel out. Right. So maybe something to do with like these top two, right? I mean, if I'm lifting something, ooh, maybe this. But these two are pretty similar to each other, right? Actually, you could argue that if you're lifting something straight up, the force you apply is its weight, and the distance you lift it is the height, right? So this you could kind of derive from it. Okay. So let's look at everything in terms of force times distance. Where this is going. Okay. So I'll say that the work in is equal to the work out. Input work equals output work. Okay. That's conservation of energy. Okay. So energy will still be conserved. Now, obviously not everything's conserved, like the forces don't match, but from an energy point of view, it would be. Right? See if this were not the case. Like if this were not true, if somehow this system could like amplify the energy, that would be really good news for us, because what that would imply is that you could have a single lump of coal supplying the entire world's energy needs. Right? You could just say, oh, let's just burn this one lump of coal, and we'll just amplify the energy over and over forever. Right? but doesn't really work that way. Right? So energy is conserved. This equal sign, you can't do that. Right? So work. Well, what is work? Wouldn't it be just force times distance? Right? And the rope moves the same way that he pulls it, so I don't have to worry about any trigonometry, cosine of the angle. Anyway, so force in times distance in equals, and the same thing over here, force out times distance out. Right? Or if you like, you could call this the weight and the height. This could be mg and h, right? mgh, weight and height. Right? But more generally, I could say it like that. Okay? Right? So, yeah. Let's run a numbers example, like the numbers right here. Right? So the output force would have been 50 newtons. That would have been like the weight, right? So I'll call this 50 newtons. Right? And let's say he has a goal of moving this weight up, let's say 10 meters. Right? Maybe he has to move it up. Maybe it's like a giant grand piano. He has to move it up like 2 or 3 stories. Well, grand piano doesn't weigh 50 newtons, but that's okay. You guys get the idea. He's got to move this up 10 meters. 10 meters. Right? So, right? How much rope does he have to pull? Do you think he has to pull 10 meters of rope? Well, let's go through energy conservation and actually find out. Okay. Now, you guys already figured out that he's pulling with how much force again? 25 newtons, right? And so let's call this 25 newtons, right? Times, let's see, distance in. Wouldn't the distance in be representing how much rope he has to pull, how much rope goes through his hands? Yeah, let's solve for that. What's the input distance? Say, how much rope does he have to pull? Can I just divide 25 newtons over? Ooh, let's do mental math. Guys, what is 50 over 25? 2. So like a 2 to 1 ratio. The newtons cancel. What is 2 times 10? 20. So wouldn't the rope that he has to pull be 20 meters? Like that? So he does have twice the strength, right? Because he can lift 50 newtons with only 25 newtons of input force. Twice the strength. But there's a catch. And the catch is he has to pull twice as much rope. So he pulls 20 meters, and thing moves up very slowly, only like 10 meters in that case. Right? But both of those are a 2 to 1 ratio. You guys see that? Right? 2 to 1 ratio, 2 to 1 ratio. But they're 2 to 1 ratios in different ways. Right? So let me give you guys some definitions. Right? They're something called mechanical advantage. Right? Mechanical advantage. And actually, I'm going to break this into 2 definitions. There's what's called ideal mechanical advantage. And like real mechanical advantage. Or on your lab page, I think I called it actual mechanical advantage, like that. So the formulas for these are a little bit different, but okay, go through this. So the ideal mechanical advantage has to do with the geometry of the system. Right? So that has to do with how much rope he pulls versus how high it moves. So this could be input distance compared to output distance. So, for example, remember how we just went through some numbers? I should have written this on a different page, so wouldn't be flipping it like this. But remember, he pulled 20 meters rope for it to move up 10 meters. Okay. Let's see how this plays into this formula. So he pulled 20 meters rope for the thing to move up 10 meters. Guess what's 20 meters divided by 10 meters? It's 2 to 1, right? Would be that reduces to a fraction. It's like 2 over 1, 2 to 1, right? So he has an ideal mechanical advantage of 2 to 1 just based on the geometry of this thing, right? Okay. Now, what's the difference between that and this other way of looking at mechanical advantage? Right? Well, actual mechanical advantage, real mechanical advantage, has to do with the ratios of the forces. Okay? But I'm actually going to see where it's like input over output for the original definition. I'm going to switch that, but you guys will see why at the end of this. Okay. Let's do output force compared to input force. Like that. Okay. That's good. All right, so let's run the numbers. You guys remember, you came up with the idea that he must be pulling with about 25 newtons of force, right? So that would be his input force, 25 newtons. The output, right, what he's getting from that is he's lifting a 50 newton force. Oh, guys, what's 50 newtons divided by 25 newtons? 2. That's a 2 to 1 ratio, isn't it? 2 to 1. So I could say he has a mechanical advantage of 2 to 1. Yeah, go ahead. Just for this one. Yeah, no, we'll look at some, we'll rig up some later that are like a 3 to 1 mechanical advantage or a 4 to 1 mechanical advantage. Yeah, you could rig up some fancy systems where you could get like a 1,000 to 1 mechanical advantage if you do it right. But, yeah. Okay. All right. Now, so why the different perspectives if it came out to 2 to 1 either way? Well, we are making some simplifying assumptions like there are no frictional losses and things like that. But what if we threw some frictional losses in here? Okay. Now, with the ideal mechanical advantage, let's say these pulleys are kind of stiff, and so there's going to be some friction that some of the energy is diverted that way. Okay. Do you think the input distance and output distance would change? No. The geometry is exactly the same. It's just based on this picture, it's a 2 to 1 mechanical advantage, no matter what, ideal mechanical advantage. But do you think that maybe you would need extra force to overcome those frictional forces? Yeah, so this guy might be thrown out of whack, the actual measured mechanical advantage. Right? So maybe he doesn't actually pull with 25 newtons. Maybe he pulls with like, what would be more realistic? 20 newtons or 30 newtons? 30, right? Because 20 is not enough. 30 could handle the 25 he ideally needs, plus maybe an extra 5 for the friction, something like that. Yeah, so maybe like something like that. So this could be 50 over 30. Now 50 over 30, that's not quite 2 to 1. Right? So 50 over 30, that's like, it's like 1.67, something like that. Huh. So maybe there's a, so 1.67 mechanical advantage, right? Maybe there's another term that we could get at to get at like proportionally how much has he lost, right? Going from like this perspective to this perspective. And that could be called efficiency. I'll give you guys a couple of perspectives on efficiency. Right? The sort of textbook definition is output work compared to input work. Right? Okay. So he puts in some number of joules, and this thing moves up, like it gains some potential energy that ideally should be the same number of joules. So if they were, like, let's say, I don't even need makeup numbers. We got it right here. Like in my example, he put in how many joules of energy? You guys see 500 joules, right? Because work is measured in joules. So 50 newtons times 10 meters, or 25 newtons times 20 meters. Either way, you're going to get 500 joules, right? Okay. So he puts in 500 joules. That's his input work, right? But, sorry, let's just go to the simple example first. Right? If you go from this point of view, both of these are 500 joules because energy is perfectly conserved 100%. You do, sorry, 500 joules. You do 500 joules compared to 500 joules, that would be 100% efficiency, wouldn't it? Okay. But something that's more realistic is that there's going to be some frictional losses. So maybe maybe he needs to input more than 500 joules. Like this thing gains 500 joules being lifted, potential energy. But this guy needs to also overcome the friction, that sort of thing. Let's go with the example if he pulls with 30 newtons of force. So 30 newtons times 20 meters, because you still pull at 20 meters, right? Wouldn't that be like 600 joules? Right? So he only got 500 joules out for doing 600 joules of work. Guys, what's 500 over 600? 500 over 600. Wouldn't that be like 83%? 83%. So that, in that particular case, that would be like 83% efficiency, right? Now, let me give you guys another perspective on efficiency, right? Which is, remember, maybe I should jot these numbers down. Okay? So just side by side here. Okay. So my example, like not quite efficient example was if he applies 30 newtons to lift 50 newtons and therefore had a, or whoops, sorry, set that up already. If he applies 30 newtons, they'd be like here. If the output force is getting like 50 newtons, they'd be like here, right? That gives them a 5 over 3 a 1.67 mechanical advantage. I can say like this 1.67 over 1, or commonly you'll see like this colon instead of a fraction bar. It's the same idea. Right? That's this actual mechanical advantage. Right? Remember, the ideal would have been the ratio of those distances. Yeah, so it should have been, any way you do it, should have been like a 2 to 1. Well, it's going to do a fraction bar 2 over 1, but you guys know this is basically like a fraction bar, right? So 2 to 1, 2 over 1. Right. So if you look at his, and okay, let's put in these numbers because I'm about to tie this all together. We see this happens, right? Also assuming that he applies a 30 Newton force, 30 newtons times the 20 meters he would have had to move it would have been, say 600 joules. So 600 joules, right? Versus he only would have been lifting it 50 newtons times 10 meters would have been 500 joules output. Right? What would that have been? 83%? You guys remember all that? 0.83, 83%? Okay, so last thing I want to do to tie this all together is that there's a different perspective you could get on efficiency, which has to do with the ratio of these two guys. Okay. What do you guys think that 1.67 over 2 is? It's 83%, isn't it? So it's a different way of getting there, but you could do this. You could say the actual mechanical advantage divided by the ideal mechanical advantage. Okay. Guys good so far? All right, so that's a bunch of good setup stuff for this lab.
If you could mix the equations for actual and then divide this by the equation for ideal, it like gives you the equation for efficiency.
Yeah. So there you go, right? Yeah. So either perspective you do, yeah, you get the same efficiency. In this case, my example numbers is like 83%. Right? All right. So, well, if you're in class, you see I've got a bunch of equipment over here. If you're at home, then I will turn the camera here in a moment. Let's see what we're doing here. It says construct a pulley system that has a 1-to-1 mechanical advantage. Sketch a drawing of that. So I think how I want to put this together. Okay. Here's what I'm going to do. I'll draw the picture first, and then I'll go rig it up. Okay. I'm going to tie a string here. So I'm thinking something a little different. Okay, that'll be right. This works. Okay. Right, so notice what I have. I have a weight over here. There's my weight. Okay. I'm just very simply slung the string over a fixed pulley, and I've got a spring scale on the other end. Ooh, so that's going to be one of our tools today, isn't it? Okay. Now, what have we got in these boxes? It says what's the weight used, what's the force reading, and then we're going to calculate those mechanical advantages, like I mentioned before. So switch over there. Okay. Well, you see how fancy this is. This is the easy lab, right? I haven't had time to disassemble this from my class. See where this is going. So we're going to work our way up to that. Ooh. Right. Just a nice simple starting spot. All right, let's use the 1 kilogram guy. No, guys, the 1 kilogram guy weighs how much again? 10 newtons, right? Should be like, well, like 9.8 newtons, but usually we say 10 newtons across. Let's measure that to make sure. Okay. Use the brown guy. Right. Yeah. Right, so this just maxes out the scale right at the 10 newton mark. Okay, so the weight is 10 newtons. Okay. So what I do is attach it here. And okay. String's a little bit too long just for the very basic setup, but that'll be right. We'll be able to make use of this. All right. And I can just pull this straight up, couldn't I? See like that? Okay. What do you guys think the force rating is on this brown scale right here? It should be 10. to see if it is, right? So we'll just hold it right here in equilibrium, check the reading. Yep, it's right at the 10 mark, right? If I pull up at constant velocity, it's also reading 10, right? As long as it's constant velocity, right? Okay, so 10 newtons. What's that?
Does it matter what angle you pull at?
Ooh, that's a good question. Does it matter the angle? Now, this is something I was going to mention later, but right here it's reading 10, exactly 10, right? Here it's reading 10, 10 on the dot, right? Here it's reading 10, yeah. So any angle I hold it at, it's also reading 10 newtons, right? Yeah, that's a really good question. Because later on today, that'll sort of be a factor, but not quite yet. Right? And the reason not quite yet is because if I look at how the weight is, if I just focus on that weight, if I made a free body diagram on that weight, there's one force down, one force up, they would have to be balanced, right? So the tension of the string should be just the weight, and in fact, the spring scale is agreeing with that. So let's switch back over to spring. All right. Here we're okay. And so the weight used, I have 3 red pens and 1 light blue pen at my disposal. Do not show up well on camera. It was 10 newtons, 10 Newton weight. And the force rating was also 10 newtons, 10 newtons. Right? Okay, so the ideal mechanical advantage comes from the geometry of the system. That's what I did. Let's do actual mechanical advantage because we have the data for that, don't we? Remember, actual is the ratio of the forces, right? So output compared to input. So what's 10 divided by 10? 1. Okay. So it's 1 over 1, or if I put the colon in there, it's like 1-to-1 mechanical advantage. So basically no mechanical advantage. If there's any advantage you get, then you get to reroute the direction of the force, and that's about it. What about ideal mechanical advantage? That's based on the geometry. In fact, all you have to do is look at that picture to get that. But the more scientific way to do it is to measure the distances. So let me show you this does work too in terms of distances. Okay. So really need a shorter string, but that'll be right. So make this work. Okay. Okay, so okay. So supposedly, however much I pull this weight up, the spring scale should move down the exact same amount, right? I can't really do that. I'm tired of that. Let me cut a shorter string just for this one. Because I want to put this next to a ruler so that you can see the weight rising as the spring scale is being pulled down. Here we go. Yeah, this is a much more appropriate length for this particular rig, right? Like this. All right. Ooh. Yeah. Last class I went with the 5 Newton weight. So it's more manageable, but this will be better for the later trials. Okay. All right, so I've had these two side by side. Supposedly with the 1-1 mechanical advantage, the ideal mechanical advantage has to do with the ratios of the distances moved. So hold this ruler right here. This could be a measuring tool, couldn't it? Let's see. Okay, so if I pull the spring scale down, let's say 10 centimeters, so from the 30 down to the 20, something like that. Okay. So pull this down 10 centimeters. How much does the weight move up? Let's see. So right there it's at the 0. Pull this guy down. to the 20, the weight moved up to the 10. So guys, if the spring scale moved from the 30 down to the 20, that's a change of 10. If the weight moved up from 0 to 10, that's also a change of 10, isn't it? Okay, so that'll lead us in ideal mechanical advantage. So let's do that. All right, so ideal mechanical advantage is also 1-to-1, and where that comes from is 10 centimeters that it 10 centimeters that the scale moved compared to 10 centimeters that the weight moved. Okay? And the actual mechanical advantage is 10 Newton weight compared to 10 Newton spring scale reading, something like that. Okay? Now, you guys see how on this particular page that I printed up, like if you did like a full-blown, like very nice science experiment, you'd actually have some data tables that would include these numbers to eventually get to that. Okay? And there's one more idea that I want to throw on here anyway, which is efficiency. Okay? Because efficiency, now I gave you guys a couple of perspectives how to get it, but they ended up being the same thing. You guys remember that? Right, so let's do this bottom one, right? The ratio of the mechanical advantages. Okay? So 1-to-1 divided by 1-to-1. Oh, guys, what's 1 divided by 1? Yeah, 1, which should be 100% efficient, right? So at least in that setup, the efficiency looks about 100%. Like that. Okay, so yeah, there's a little bit more I wanted to go over than exactly what's printed on the page, but you guys got any questions so far? Okay, now here's where I want to pause to let you guys think ahead a little bit. Okay. There are a couple of recommended questions I have. Now, when you guys do this lab write-up later today, I'll give you guys a few minutes in class to do this. I want you to come up with a question. Okay. You can come up with anything you want that you could use with this measured with this data, but here are my recommended questions. Right? So one recommended question might be like, what is the actual mechanical advantage of, and then pick one of the pulley systems, like for example, the 3-to-1 ideal mechanical advantage pulley system. Right? So what is the actual compared to ideal, something like that. And you could refer to a figure, so you could say, because AP will let you do that too, right? Sometimes they say, oh, like draw a figure and refer to the figure, and then that could be maybe something like this. Right? Another good question you could ask is, what is the efficiency of, and then blah, 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 same idea of maybe the ideal 3-to-1 mechanical advantage system. What is the efficiency? Okay. Now, we've done one that came up to 100%, so that was pretty straightforward though, right? If you want to do a different type of question, I guess there are some other questions you could think of, but those are 2 pretty good ones. Okay. Let's do a 2-to-1 mechanical advantage. Okay, 2-to-1, and then same thing. So same story with all these. All right, now 2-to-1. Okay. Now this is about to get more exciting. There's something new about to pop up here. Oh, also your starter question, that was an example of the 2-to-1 mechanical advantage, wasn't it? Right? The guy pulling that rope. Right, that's about what we're going to do right here. The other day, I thrown some of these red pulleys on your guys' desk so you could get your hands on them. Right, so, for video anyway. You guys remember these pulleys are, well, it's a single pulley. These wheels spin really easy. There's a groove so I can pop the string in. Okay. No, the ones I've got rigged up here are just single pulleys. Okay. But later on, we'll make use of this guy. He's a double pulley. And these pulleys can move independently of each other. So one can go clockwise, the other counterclockwise. So not quite ready for that guy yet, but later on. So pop the string back in this groove. Got my spring scale right here. Guys, go ahead and make a prediction. What do you think the spring scale is going to read for this right here? Oh, you guys are saying 5 newtons? Ooh, I like that prediction, 5 newtons. Because ideally, there should be a 2-to-1 mechanical advantage, right? Is that? Oh yeah, spring scale's reading. You know what? Is this calibrated right? Huh. I think it is. It's reading more like 5.2. All right, let's go with that. I guess 5.2. We'll see how it plays out. Okay? So I'm pulling 5.2 newtons for it to do this, right? Now, some things you see is obviously this force is about half of this force, so 2-1 mechanical advantage. Okay? But look at the distances that these things move too, because notice how I'm pulling the spring scale up a lot versus this wave's moving very slowly, isn't it? Ooh. So that's also a 2-to-1 ratio, but like the opposite way. And now it's no wave. Try that again. I wanted to mention that, did you guys see that one of those pulleys was also moving up and down? Right? That was called a movable pulley. Single movable pulley. Okay. Oh, my string is entangled too. Really, huh? Yeah, all right, let's play the untangle game. Ew. Yeah.
Why are those things heavier?
They're probably made for other things. But yeah, you're right though. If these stamps were heavier, one or the other, yeah. Harder to tip them over, and if they did tip over, yeah, give us a nice hole in the floor. Okay. All right, so you guys see how this pulley is actually moving up and down? Right? Versus later on, we might make use of these guys that are just hanging out here. So the ones that are stuck in place could be called fixed pulleys, but this guy is not a fixed pulley. You guys see how it's moving? It's called a movable pulley. Okay, it's actually moving along with the system. Okay, okay, and let's make a measurement where put the ruler next to both the spring scale and the weight to see how the distances compare. Okay, man, you know what? It's kind of hard to measure that way, so I'm going to reroute this one more way. Okay, let's bring in this guy right here. Okay. What I showed you was a 2-to-1. Let me make one more fancy change. No, this is still a 2-to-1. You guys do see that, right? Still 2-to-1. Hey, where'd my list go? Aww. Ooh, yeah, why is it still a 2-to-1? Right? If I get the 3 tied, we will take a look at why this would still be a 2-to-1. Huh. There we go. Right. So supposedly this is still a 2-to-1, right? Because in fact, if you focus on the movable pulley, you can usually figure out pretty fast what the mechanical evasion is going to be. Because think about free-body diagram from this point of view. Right? So free-body diagram. I got one force acting straight down. I got two forces acting up. But you have a 2-to-1 ratio, couldn't it? Okay. So the force still splits 2 ways. Right? This force rating right here is still, it's still straight over 5 newtons. It's like 5.2 newtons. Huh, that's interesting. 5.2 newtons. Okay, I get this. Okay. Now it's a lot easier to make the side-by-side measurements. Okay. So let's see if I pull the spring scale down, get these kind of side by side here. Okay. So right now the top of the hook is reading at the 20 centimeter mark. But if I pull it down to like the 10, now let's go all 20, like that. So for this thing to go 20 centimeters, what happens to the weight in the same place? Because right now the weight's at the 0 mark, bottom of the weight is. So for me to pull this down 20 centimeters, the weight went up to the 10 centimeter mark. So 10 centimeters compared to 20 centimeters. So it's like a 2-to-1 ratio. Okay. And what did I get this to now? I'll hook it to itself. It's strange. This one. All right. All right. So what are we looking at? I rigged up a couple of systems. I'll draw the one that I have right now. The last one I did. So there was a movable pulley and also a fixed pulley. Right? And then the string was tied here, wrap it underneath the movable, over the fixed. And the idea of throwing this fixed in here is that I can reroute the string so that I can pull down. Maybe if I'm like down on the sidewalk and I'm trying to lift a grand piano, something like that. Here's the weight, something like that. Okay. So I pull down this way, and it lifts the weight. Okay. Right. So the weight that I used was 10 newtons. Right. The force rating was like 5.2. Right. So now the ideal mechanical advantage from, and this came from a movement of 20 centimeters compared to movement of 10 centimeters, would be a 2-to-1 ratio, 2-to-1 mechanical advantage, ideal. Right? You could get that just from the picture anyway. Should be 2-to-1, right? 2-to-1. Right? But the actual mechanical advantage comes from dividing these two guys out. 10 Newton output force compared to 5.2 Newton input force. Let's see what that would have been. It's 10 over 5.2. I'm looking at 1.92, and then it'd be a fraction, so over 1. The fraction I'm going to represent as a colon, just because a lot of times it's written like that. Okay. So, the ideal mechanical advantage should have been 2-to-1, but it looks like it's closer to like 1.9-to-1. So this is a little bit of a lossy process, isn't it? Not getting the full bang for my buck here. How could you quantify that? Well, maybe something to do with like efficiency, right? Efficiency. So maybe I should divide these two numbers out. Right? What is 1.92 divided by the actual mechanical advantage compared to the ideal mechanical advantage? I'm getting 96%. Right? Get that? Like 96% efficiency. Okay. Now, if under lab right up, if you went with the efficiency question, then you would want to explain where you got those numbers from. Of course, so ideal, the actual mechanical advantage divided by the ideal mechanical advantage. That's how you would get efficiency. Okay? Or working with the other way. All right, next one, 3-to-1 mechanical advantage. Let's do 3-to-1. 3-to-1. All right, well, I could probably continue off what I had, except that now this string is actually getting kind of too short for what it needs. So let's go back to the long string. Right, remember, start off with that really long string. Right, I think I want to put this together too. Yeah, and I'm just going to disassemble this whole thing. It must be done. Save that for next class. This guy. All right, guys, what mechanical advantage is this right here? What is that? Hold on. 2-to-1. This is exactly what I had before, right? Just a long string. Okay, I just want you guys to see that starting off. Still 2-to-1. Now, how can I reroute the string to somehow get 3-to-1? Well, I probably need to look at this movable pulley. I mean, look at the movable pulley. There's 2-to-1 right there. If only I had 3, that could fix my problem, right? Do 3-to-1. You guys just look right here. I mean, a big thing with labs is like actually getting your hands on the stuff and like trying to route the string and tie it and stuff. But, yeah. We got quarantine version, so doing what we're doing. So, if I could somehow maybe reroute this end to loop around and come back and hook right here, that could do it, couldn't it? Let's do that. Let's do that. So I'm going to play off this here fixed pulley. Okay. Oh, let's try to flip this. No. Hold on. Nope, that didn't work. Hang on. Time out. Technical fix. Those things you run into with stuff like this. Let's keep this guy grounded for a moment. Okay. Now, ooh, look at this. Look how I can use a 5-Newton weight to hold up a 10-Newton weight. Ooh, and you just barely hold it. Just barely holds it. The only reason it's accelerating even is because you're adding the weight of the spring scale. Right? so it's slightly weighted to, ooh, that's pretty close. But the reason I'm stopping this thing and pausing is because this knot is slipping. So let's do like a square knot on this guy. I should hold him in place. I think. Or am I just being, no, I'm just being crazy. Try this. We knock on top. Okay, wow. That better hold. Cross our fingers. That's how we do science. Okay. So we're going to bring this down, hook it in this middle hook. Get rid of this guy's just excess. Okay. All right. Look at that. You guys see 1, 2, 3 up, like 3 to 1. Like 1 weight down, 3 strings up. That should be a 3-1 mechanical advantage, shouldn't it? Yeah, something like that right there. Separate this out, make this a little bit more. Oh yeah, that looks a little cleaner, doesn't it? And this guy's. Okay. All right. What do you guys think the force rating is on this Brown scale right now? Yeah, probably about 3.5, somewhere there. Right? That makes sense, right? Because 10 newtons divided by 3 should be about 3.3. But let's see what it actually is. It is actually reading 3.5. 3.5. Ooh, 3.5. Okay. Yeah, look at that. Okay. So they're very close to the 3-to-1 mechanical advantage, maybe slightly less actual ratio of forces. Let's do the whole ratio of the distances moved thing. So let's try this again. Okay. So when the spring scale moves, try to keep this as still as possible. Get this zeroed out. Okay. What if I move this guy down? Move him down the full length of the roller? Just barely. Yeah. Okay. So I can move the spring scale 30 centimeters and the weight moved from the 30 mark to the 20 mark. Okay. So the spring scale moved down 30. So weight went from the 30 to the 20, which means that it went up 10. Oh, that is a 3-to-1 ratio, isn't it? And so for this to come down 30, this only went up 10 centimeters. That's a 3-to-1 ratio, right? You guys got that? Okay, so let's fill in this box right here. So I've got, get this picture going, got a ceiling. All right. Now, I do have a couple of fixed pulleys and 1 movable pulley, right? Guess what? Now, the movable pulley, that's the one the weight's directly attached to. It's got a hook on top of it. And around the string, one endpoint of the string was on that hook, on the movable. Wind it around this way, this way, this way, this way. And then spring scale is on the other end. Yeah, see some faces.
If you had a 3.5 weight, would it be balanced?
Oh.
3.5 would be in there.
Huh. Yeah, so Morgan's asking a pretty good question, which is, so we used a 10 Newton weight. The force rating was 3.5 Newtons. Right? So what if there was just 3.5? Would that hold steady? It would. Now, there are some losses in here. Like, obviously, this isn't, like, if this were exactly efficient, this should be like 3.33. So it's a little bit lossy. Maybe there's some friction losses, possibly. So what I'm thinking is, it has to do with maybe the direction of the friction. I think it might just barely hold it in place. But if the friction switched the other way, then, well, then it would just like fall the other way. Right? So yeah, wouldn't really count on that, but it might just barely. There's another place there's another place you could lose some efficiency too, which is not in friction. But yeah, well, let's talk about that now. Right? It's really to the question you asked earlier about the direction. Remember, like the first one, I could change the direction of the spring scale and it made no difference at all. Right? But it says we're going to come back to that idea because see with the first two, see how the strings are straight vertical, like this one's straight vertical, these two are straight vertical, right? Part of what we're assuming is that these strings are vertical versus the 3-to-1. Well, if you look at either my rig in class or my picture, these aren't exactly vertical, they're just pretty close, right? Right? Now, why is that important? You guys remember that spring scale lab we did back in the day? Okay, here, let's do a quick reminder. Let's call gravity is this way. Gravity's pointed towards me, like it's down. Okay? And one of those 10 mini labs that we did was I had you guys make this Y shape, then start taking the top two and pull it closer, more horizontal, like a T shape. You guys remember that? What was happening to the force and spring scales as I was pulling more and more like a T shape? Greater and greater. Remember, you can never make a perfect T because a perfect T would be like infinite force, right? Right. So because you have to carry the vertical loads, right? So think about free body diagram on this guy. Okay? I'd say that okay, if it's like 10 newtons down, these guys have to carry the vertical 10 up, so split 5 and 5 just for the vertical part. In fact, if it's all vertical, it should be like 5 and 5 exactly. Okay. But if I make it like a Y shape, or there's some horizontal component, then the vertical components are 5 and 5. But then there's some horizontal components. Right? So you have, if you focus on, let's say, the yellow scale, make it like a right triangle, right? And then the more you make it to a T, the horizontal increases. The total force is the hypotenuse of that triangle, right? Something like that. Okay. Yeah. So we're kind of running into that situation here, where maybe some of the additional force is because these strings aren't exactly vertical anymore, right? So that can also knock off some of the efficiency of the machine. Right, so ideal mechanical advantage, of course, should be 3 to 1. You guys figured that out, right? Okay. Now, we did do the measurement, so really strictly where that comes from scientifically is 30 centimeters compared to 10 centimeter movement. Okay. The geometry, you guys see it would be that anyway. The actual mechanical advantage, you guys know we're going to do 10 newtons compared to 3.5 newtons. What's that? It was 10 over 3.5. I'm getting 2.86, and you can say to 1 if you call it a fraction. Okay. So 2.86 to 1 mechanical advantage. Okay. So then to finish this off, efficiency would be, would it just be the ratio of this? So it is 2.86 compared to 3, right? The real compared to ideal. Okay. I'm getting a 95% efficiency. Ooh, pretty close to what it was in the last one too, right? In fact, it looks like every time I route the string over more pulleys and do more fancy stuff with it, the efficiency is dropping a little bit. Not a whole lot, but a tiny bit, right? 100% to 96% to 95%. You guys okay. All right, and now we're at the last one, 4 to 1. Here. Okay, so see 3 to 1 one more time because you want to see that. You're thinking, yeah, these strings really aren't quite vertical or right, something like that, right? All right, 4 to 1. How can I modify this? Yeah, sweet. So how can I modify this to be a 4 to 1? Okay. Well, what I'm thinking is, I remember when I needed to go from 2 to 3. Remember this was 2, and I just took this, which is hooked over here, and just rerouted it over this guy. Right? Oh, that's what I wanted to mention too. Okay, guys, how many fixed pulleys do I have, and how many movable pulleys do I have? There you go, 2 fixed and 1 movable, right? Get that? Okay. So maybe I could modify this into a 4 to 1. Maybe what I would want to do, could you guys imagine if I unhooked this string right here and rerouted it underneath the movable, and maybe hooked right here, right? I have 4 strings going up from the movable, right? Like 2 and 2. Right? Now, if I do that though, then see, I have a single pulley right here. Versus if I had a double pulley, that would be really good because I could route the string under one of these grooves and then reroute the other under the other groove, right? Let's do that. So I'm going to pull this movable out. I need a relief picture situation. Pull this guy in. Back there. Right. So there's a 2 to 1 mechanical advantage. Okay, this guy's just barely holding it right now. Ooh, yeah, it's pretty well balanced, isn't it? Route it over this guy. Now we're up to a 3 to 1. Remember the 2 to 1 is just balanced, so these were pretty well evenly weighted. Now it's 3-1. Well, no, well, I didn't expect it to be that exciting, but I did expect this guy to win, just not by that much. So now the little guy definitely wins. He's got a great mechanical advantage. But we're going to go one more step here, which is we're going to unhook this guy, route it underneath the other movable pulley, or sorry, the other wheel of this movable pulley. And to this guy, or can hook, just so it's hooked. If you look really close, you guys see 4 strings going up from the movable. So 1, 2, 3, 4. You guys see 4? So it'd be like a 4-to-1 mechanical advantage. At least ideally it should be 4-to-1. Okay. Let's check what it is ideally. If I put these guys side by side, you guys see how the spring scale's moving really fast and the weight that's being moved is moving really slow? Okay. Let's see what the ideal mechanical advantage would be. Of course, it should be 4-to-1. Okay. I hope it is. Okay. Let's see. Since I predict that, I'm going to start the top of the scale at the 28 centimeter mark because 28 is a multiple of 4. Right? So if I move this guy down the full 28 centimeters, move down 28, right? Make sure the weight's zeroed out. You have the bottom of the weight at the 0 mark, so this guy goes down 28. The weight moves up to the 7 centimeter mark. So 28 centimeters down versus 7 centimeters up. Right? That is exactly 4-to-1. Obviously, it should be. Okay? Let's look at actual mechanical advantage, the real mechanical advantage. Okay? So, what is the reading of the spring scale? The reading of the spring scale is, see, it's about, I wanted to say 2.7, but now that this force is getting so small, maybe I should actually pull in the green scale. I'm thinking about it. Because these forces are getting pretty small at this point. This might give me a more accurate reading. Well, it's telling me the same thing though. Yeah, it's like 2.7. Yeah, 2.7. Okay. So we got, gotta draw this thing. Okay. So you guys saw, I have a ceiling here. Okay. I have a couple of fixed pulleys, fixed. Okay. I have a movable pulley that's actually a double pulley, so just keep that in mind. Okay. Got a weight right here. That. Okay. Then how did I wrap the string? Okay. Well, I went from this hook down below the movable pulley, over this fixed, down underneath the movable again, just through the other groove, and then over this fixed finally, just so they can reroute the force so I can pull basically down. Right? Like again, if I'm down on the sidewalk trying to lift the piano, something like that. Okay, so I see 1, 2, 3, 4 strings going up compared to 1 weight down. Okay, the weight used was 10 newtons. The force rating was, I said 2.7, right? 2.7 newtons. Okay. The ideal mechanical advantage would have been 4-to-1. Remember where that comes from. It came from 28 centimeters that the spring, the spring scale moved compared to 7 centimeters that the weight moved. Okay. That's really the origin of that number. And then the actual mechanical advantage would be whatever 10 newtons divided by 2.7 newtons is. So it's 10 over 2.7. Okay. That's 3.70. Like 3.70 to 1. So it should have been a 4-to-1 mechanical advantage. In reality, it came out to about 3.7 to 1. Okay. So then the efficiency. Did I tell you guys that efficiency a lot of times is written as this Greek letter? Should look that up. Maybe we'll Google that real fast. I think it's called nu. Let me see. No, I'm thinking of something else. Okay. Not quite sure what I would Google to get that.
You
oh, no, sorry, I was saying, yeah, you're right. Me would be. This is, I forget what it's called. Sorry, guys. Okay, so anyway, it ends up being, yeah, it does stand for efficiency. Looks like an N with a long tail on it, right? Whatever 3.7 over 4 would be, right? Because 3.7 to 1, 4 to 1, right? See what that would be. Looking at 92 point something percent, rounds to about 93%. Right? Okay. Guys, with it?
Google says it's Ada.
How do you spell it? ETA?
Yes.
ETA. That sounds right. That rings a bell. ETA, Greek letter. Yeah. Thanks, Morgan. Nice find. So, yeah, so this is Greek letter eta that a lot of times, well, can be used to represent efficiency. Right? There you go. Any questions about any of those? All right. So, give you guys a few minutes in class to do a lab write-up. Now, on the back of this page, it's blank, so you guys can do that. Did mention a couple times that, yeah, if we went back and redesigned this lab, I'd probably include like a lot more data tables so that there's like more convenient place to put some of those numbers. Okay? But write your lab write-up here. Give you guys a few minutes. Here's the format. So, what question do you want? Remember, I threw a couple of recommended questions at you guys, so I do recommend you pick one of those. But if you think of something else, then go for it. What measuring equipment would be involved? Because what measuring equipment do we use in class? Spring scale and the ruler, right? Because we were measuring, so you could say ruler or meter stick in addition to the spring scale. Those were two pieces of measuring equipment. Procedure to gather the data. Remember, if you're looking for like 3 to 6 steps somewhere there, you can refer to a diagram. In fact, this would be a really good opportunity to refer to a diagram, to see diagram on the other side, right? And then now once you've gathered the data, this is where I was reading about you guys' lab write-ups. Some of you guys were sort of mixing these steps into just one giant idea. Right? So this third bullet point specifically, what are you going to do just to gather the raw data? Right? I'm going to use this equipment to get this equipment to get this. This fourth step is more about like, okay, once you have the data, how are you going to, what are you going to do with that to answer your question? Maybe you're going to make a graph, maybe not this lab, I don't know, unless you're really, really creative. Maybe there's an equation things could feed into. We did a bunch of equations today, didn't we? Right? Something like that. Right. And then you can draw some kind of conclusion, like, say, well, depending on what you're looking for, mechanical advantage, efficiency. It's like, the efficiency of that 3-to-1 system would have been blah, blah, blah. Okay, so I'll give you guys a few minutes to do that. Okay. One question, and yeah, I do recommend that you just take like one of the big ones, just a 3-to-1, and just focus on that.
For the recommended question, are you writing this conceptually, like for any, weight or like size strength scale or specifically?
Oh, yeah, so, I'll let you figure that out. Right. Whether you want to say something in general or something specific, because, yeah, then you might, in your data gathering part, like do slightly different things. So, yeah, so go ahead and hone in on one of those questions, and then depending on how you phrase the question, procedure could be a little bit different. All right, so it looks like some of you guys are finished, or you guys are getting pretty close. So, is before you walk out of class today, we've got a few minutes left. Before you walk out of class today, throw your lab write-up in the grade tray, or if you're online, you can upload it to Focus. Here in the last few minutes, I'm going to ask you guys some conceptual questions. You guys remember back on Monday, I gave you guys a page of conceptual questions? Right, so I think I gave out all my extra copies, otherwise I would project them up here. Right. Also, I can't project my computer screen, so otherwise I would do that too. Right. But if you have those, if you want to follow along, I'm just going to go over these in the last few minutes of class. If you're still working on your lab write-up, then go ahead with that. Finish with that then. Right, here we go. So first question says, in physics, work is defined as, and you guys know work is defined as? Yeah, force times distance, right? Yeah, force times distance. Right. So the second question says, if you push with twice the force for twice the distance, then how many times the work have you done? Work is equal to force times distance. If you push on something for twice the force, for twice the distance, how many times the work have you done? 4 times. You guys see 4 times? Factor 2 times a factor 2 is 4 times. See, the unit of work is, you would say, joules. Right? There are lots of ways to measure energy and work. We'll just stick to joules right now in this class. Power is defined as, would you guys say, work divided by time? Right? Power is work per time. And the unit of power is the watt. Right? Let's talk about these units a little bit. Because energy, we're going to use joules, measured in joules. Right? But if you get a bill from an electric company, they usually don't say joules, they usually say what? Like kilowatt hours. You guys have seen kilowatt hours? What does that mean? Well, you guys know watts is a unit of power, right? So power, hours, isn't that like a unit of time? And kilo, isn't that just a prefix, like 1,000 times? Kilo is a factor of 1,000. Oh, power times time. Well, if power is work per time or energy per time, then wouldn't be power times time bring you back to like work or energy? Yeah, so that's what kilowatt hours means. Right? So if you get a statement, so it's like, oh, you use so many kilowatt hours. Right? It's just a really convoluted way to talk about energy, but it is an energy unit, isn't it? Then this class we're going to use joules, but FYI, it's let's see. The amount of potential energy possessed by an elevated object is equal to, and one of the options says the work done lifting it. I like that answer. See, some other options are the distance lifting it, the force used to lift it, the power used to lift it, but potential energy, okay. Got this object sitting up here, okay. Has some mass, has some height, it's in a gravitational field, the potential energy is mgh. Okay. The reason it's the work done lifting it, well, that's the only one that makes sense out of those options anyway, because work and energy have the same units, they're both in joules, so it's the only one that's even consistent. But to lift it from here to here, I have to apply some force, which would be its weight, times some distance, which would be its height. Yeah, so the work done lifting it is equal to the potential energy that it ends up with. Kinetic energy. Do you guys know the formula for kinetic energy? Memorized?
One,
One half mv squared. There you go. Uh, how much further will a car traveling, let's say, 100 kilometers an hour skid compared to one going 50 kilometers an hour? Okay, let's draw this out. So I got a car, let's say it's going 50 kilometers an hour and slams on the brakes and comes to a stop. Some distance x. Then goes back and redoes this whole thing, but that has twice the initial speed. Guys, if you double the speed in the car, what happens to your stopping distance? It gets quadrupled, doesn't it? Yeah. Okay. So it gets bigger, but it's not a 1-to-1 ratio. And it comes from conservation of energy. The sum of energy initial, the sum of energy final. Okay. So what kind of energy does the car have starting with? Kinetic. That's like this right here. Right? Notice what I'm doing. Right? I'm just going back to this. Just like the 3-page table we did a couple of days. Right? Got these 4 building blocks. Boom, there's one on building blocks. Right? And then where did all the energy go? Into the work done by friction to slow the car down. Or well, I shouldn't say D, I should say X, because my picture has X. Right? Force times distance. Right? And then see, mass doesn't change, the friction force doesn't change, but there is a relationship between how fast and how far. Right? And it's a squared relationship. So yeah, every time you, so if you double your speed, you'll have 4 times the stopping distance. Triple your speed, you'll have 9 times the stopping distance. You guys remember that? All right. There's a question about a pendulum swinging back and forth. A pendulum swinging back and forth. Right? And then it says which would be true, and it talks about potential and kinetic energy. So there's a vertical line, there's a pendulum, swing, swing, swing. Maybe 3 different photos they take. There, right? Swing back and forth. If I define height 0 to be the bottom of the pendulum, because that's as low as it can go, that's a pretty convenient place to define height 0. Then at the bottom, it's definitely in motion. It has all what kind of energy? Kinetic. It's 100% kinetic. What about the endpoints? Is it moving here? Nope. So it has all what kind of energy? Potential, MGH, because there's some height been lifted up here, right? And they'll just transfer back and forth, right? Potential, kinetic, potential, kinetic, potential, kinetic, and just goes up there, right? Paul Hewitt, your textbook, my old materials might say PE for potential energy, KE for kinetic. So if you ever see that notation, you know what that is, right? The new notation is capital U and capital K, though. Okay. A question says, if an object has kinetic energy, it must also have, okay? So let's say I got a baseball, has some kinetic energy. Does it have a velocity and a mass? Yep, because 1/2 mv squared. Okay. Now what else does it have to have a force maintaining it? No, right? No, a force would change its speed, but it can have constant speed, right? Does it have to be accelerating? Nope. Okay. Does it have to have momentum? Now, momentum we'll talk about next week. Momentum is mass times velocity. You guys see how momentum and kinetic energy, P stand for momentum. See how they have the same ingredients, both mass and velocity? Ooh, so if it has one, I bet it has the other. All right, so go ahead and pop your lab in the gray tray, and bell's about to ring. This is next week's stuff. All right, so have a good rest of your Wednesday, and I'll see you guys tomorrow for AP Classroom. We'll go over the most missed questions on AP Classroom tomorrow.
Have a great day.
Yeah, have a good day, guys.